Bismillah ar-Rahman ar-Rahim. I will talk about the probability density function and characteristic function of a random vector Z. Z is Gaussian, complex valued, circularly symmetric. It has a mean vector mu Z and a covariance matrix CZZ. Z can be written as x plus iy. Now x and y, those are real valued and n-dimensional. They are jointly Gaussian. So each one of them is Gaussian. X is Gaussian. It has a mean vector mu x and a covariance matrix CXX. Y is a Gaussian random vector. It has a mean vector mu y and a covariance matrix CYY. Now the mean vector of Z is take expectation, and so this will be the expectation of x mu x plus I times the expectation of y mu y. The covariance matrix of Z, because Z is a complex valued random vector, then its covariance matrix is the expectation of Z minus its mean vector times Z minus its mean vector Hermitian. And so Hermitian, for the real valued vectors, we use transpose. So this is a column vector and its transpose is its row version. But here we do not just transpose, we transpose and take the complex conjugate. So this is the definition of the covariance matrix in the complex case. CZZ is expectation Z minus its mean vector times Z minus its mean vector Hermitian. So Hermitian, it involves two operations, transposition and complex conjugation. Now let's write down the covariance matrix of Z in terms of the covariance matrices of X and Y. So Z minus mu Z, Z itself is X plus IY, and the mean vector of Z is the mean vector of X plus I times the mean vector of Y. So Z minus its mean is X minus mu X plus I times Y minus mu Y. Now we will take this vector here and we multiply by its Hermitian. So the real part, so this column vector, it becomes here transposed. This column vector is also transposed, and then there is a plus I, it becomes minus I. Now we multiply the two brackets, and so we get X minus its mean vector, and from here X minus its mean vector transpose. So when we multiply and apply expectation, that's the covariance matrix of random vector X. Plus I times minus I, that's 1. And then we have Y minus its mean vector times Y minus its mean vector transpose. Apply expectation. This is the covariance matrix of the real valued random vector Y. That's CYY. Then we will get cross terms. So here we will have I, and we have expectation of the vector Y minus its mean vector. So this is a column vector of size n by 1. And this is multiplied by X minus mu X, X minus its mean vector transpose. That's a row vector 1 by n. And so we get an n by n matrix. This is the cross covariance matrix between random vector Y and random vector X. And so this is CYX. And we will get the fourth term, which is the expectation of X minus the mean vector of X. And from here, we take Y minus the mean vector of Y transpose. And this will give us the matrix CXY, which is the transpose of the matrix CYX. So generally speaking, if we have a complex valued random vector, its covariance matrix in terms of the covariance matrix of its real part, the covariance matrix of its imaginary part, and in terms of the cross covariant matrix will be given by this CXX plus CYY plus ICYX minus ICXY. Now, vector Z of interest is circularly symmetric or proper. And what does it mean for a complex valued random vector to be proper? So in this case, we define a proper complex valued random vector as a vector whose pseudocovariance is all zero. And so we define something called the pseudocovariance matrix. And the definition of pseudocovariance is very close to the definition of the covariance. It is just that we replace Hermitian here, which again is transposition and complex conjugation. We replace this just by the transpose. So the pseudocovariance here I denoted by CZZ tilde. And so it is not the true covariance. That's the reason we have here pseudo. It is a pseudocovariance, and it is called pseudocovariance because its expression is very close to the expression for the covariance matrix, but it has this difference here using the transpose rather than Hermitian. Now, the pseudocovariance, you can just compute it as we did above for the covariance. For a complex valued random vector to be proper, the pseudocovariance must be the all zero matrix. So this is the definition of a proper complex valued random vector. It has a pseudocovariance matrix that is all zero. Now, if we evaluate the pseudocovariance, what is the difference? Because here we are using Hermitian, this is minus I, because we take the Hermitian of this vector here, of this column vector. So the real part gets transposed, the imaginary part gets transposed, and plus I becomes minus I. Here we do not do complex conjugation, and so plus I here remains as is. And so when we multiply the two brackets together, we will get CXX when we multiply these two guys, this, and apply expectation. But then when we multiply y minus its mean vector by y minus its mean vector transpose, these two guys are multiplied by I squared, which is -1. So here we will have cxx minus cyy, and then we will have plus I cyx plus I cxy. So here compare between the covariance, the true covariance of the vector, and the pseudo-covariance. The pseudo-covariance can be computed for any complex valued random vector. But if we want our vector to be proper, or in the Gaussian case, we say that the vector is circularly symmetric, then the pseudo-covariance matrix must be equal to the all-zero matrix. So if I have a matrix here, it's equal to the all-zero matrix, then the real parts are all equal to 0, and the imaginary parts are all equal to 0. So this cxx minus cyy must be the all-zero matrix, and hence, for a proper complex valued random vector, the covariance matrix of the real part is equal to the covariance matrix of the imaginary part. Cxx is equal to cyy. Moreover, we want cyx plus cxy to be equal to the all-zero matrix, and this means that for a proper complex valued random vector, cxy is minus cyx. Recall from the definition that cyx and cxy are the transpose of one another, so it means that cxy is Q-symmetric matrix. If our complex valued random vector is proper, now rather than using 4 different matrices, now we can just express the covariance matrix using 2 matrices, because cyy is equal to cxx. So these 2 terms now can be combined as double cxx. And because minus cxy is cyx, again, we can write here plus 2i times cyx. So czz now has a simplified expression, 2cxx plus 2i times cyx. Now, if we want the distribution and the characteristic function of vector z, what does it mean that we write down the PDF of a complex valued random vector? It simply means that we write the joint distribution of the 2n real valued random variables that enter into the composition of this complex valued random vector, right? So we have vector z, and vector z, it contains 2n real random variables. So x1 plus iy1, x2 plus iy2, all the way to xn plus iyn. So when we talk about the joint distribution, the joint PDF or the joint characteristic function, we are talking about the joint distribution of those guys, x1 and y1 and x2 and y2 and xn and yn. So the distribution or the characteristic function, it means that write down the distribution or characteristic function of the 2n real valued random variables that live in or reside in the complex valued random vector, which is called z in our case here. So for the PDF and the characteristic function, and since we are talking about a Gaussian random vector, then we have formulas. I will take for granted that we know the formulas for the multivariate PDF and CF in the real case. So the PDF is what? The PDF is 1 over 2 pi or square root 2 pi, and then you have power here, and you put here the dimension of the random vector. And then we have the square root of the determinant of the covariance matrix. And then we have exponential, and then we have minus 1/2, and then we have a quadratic form, the vector minus its mean value transpose. Then we have the covariance matrix inverse, and then we have the vector minus its mean, the random vector minus its mean vector. So if we apply this to our case, we have 2n real valued random variables. We can stack them on top of one another in vector w. Now everything is real now. We don't have complex anymore. So what is the PDF of this? It's 1 over, and then we have square root 2 pi raised to the power the number of random variables that we have here. We have 2n of them. So we have square root 2 pi raised to the power 2n. So this will give us 2 pi raised to the power n. And then we have a square root, and then we have the determinant of the covariance matrix of this random vector, which here is called CWW. So this will be the covariance matrix. And if we take the vector times it's a transpose because this is a real valued random vector, then if we do the product, we have here x minus its mean vector times x minus its mean vector transpose, apply expectation, that's cxx. X minus its mean vector times y minus its mean vector transpose, apply expectation, that's cxy. And then here we get cyx, and here we get cyy. And this is the general case, but we are interested here in a complex valued random vector that is proper, which means that the x vector and the y vector, they satisfy these two relations, that cyy is equal to cxx and cxy is equal to minus cyx. So we can write down the covariance matrix CWW just using the matrices cxx and cyx. What about the characteristic function? So for the characteristic function, we have, in the Gaussian case, we have exponential, and then we have I, and then we have an inner product between the mean vector. So the mean vector in our case here is, we can put mu x on top of mu y. That's a 2n by 1 column vector. And then we have 2n variables, 2n real variables. N of them are in this vector u bar. I will put it here, transpose, u bar transpose, and the other n are in u tilde transpose. Then we have minus 1/2, and we have a quadratic form. This quadratic form, the covariance matrix of vector w, which is this vector here. And then we have our vector u. So vector u, I divided it into 2 halves. The top half, u bar. Here we have n components, and then u tilde, another n components. And here we put the row version of this vector. So this will be u bar transpose, u tilde transpose. This is the joint PDF, and this is the joint characteristic function of x and y. But we combined x and y in the complex valued random vector z. And this is for the sake of having a compact representation. Rather than working with x and y, we just combine them as one complex valued vector. And so it would be nice if we can rewrite the PDF and the characteristic function so that everything is in terms of vector z, its mean vector, and its covariance matrix. So I want to write down something like f of z, like this, or a characteristic function for vector z. The meaning is what you can see here. The meaning of the joint PDF or joint characteristic function of a complex valued random vector is indeed the joint PDF or joint CF of the components, the real and imaginary parts of the components of vector z. So if vector z is n dimensional, we are talking about the 2n real valued random variables that reside inside vector z. But again, for compactness, and since the objective from the beginning is to deal with x and y as a unit, as one unit, which we call z, it would be nice to have formulas, expressions for the joint PDF and the characteristic function that only make use of z, mu z, which is mu x plus I mu y, and then czz. To be able to express the PDF and CF in terms of z and its statistics is to think about the eigendecomposition of the matrix czz. So czz is a covariance matrix. And because it is a covariance matrix, then it is Hermitian. And because it's Hermitian, then all its eigenvalues are real valued. So here, lambda, which is an eigenvalue of czz, all eigenvalues are real valued. In fact, czz is positive semi-definite, which means that the eigenvalues are not just real valued, they are non-negative. In fact, we will take the eigenvalues to be strictly positive so that matrix czz is assumed to be invertible, and we can write down the PDF in terms of the inverse of czz. So czz, again, is a Hermitian positive definite matrix. It is diagonalizable, and its eigenvectors can be constructed so that they are orthonormal. All the eigenvalues of czz are real valued and positive. Generally, they can be 0, but here we will take all of them to be positive. If lambda q is an eigenpair of czz, then czz q is equal to lambda q. Now, write down everything in this eigen equation in terms of the real and imaginary parts. Czz is equal to 2cxx plus I 2cyx. Q, I will write Q as QR plus IQI. Lambda is real valued, again, because the matrix is Hermitian. Q again, then we have QR plus IQI. We can divide both sides by 2, and so we have CXX plus ICYX times QR plus IQI is equal to lambda over 2 QR plus IQI. Now, multiply these two brackets and equate the real part on the left-hand side with the real part on the right-hand side, and do the same for the imaginary part. Doing this, we get the following two equations. CXXQR minus CYXQI is equal to lambda over 2QR, and CXXQI plus CYXQR is lambda over 2QI. Now, construct a 2n dimensional vector by taking QR over QI. So this is what we'll do. We'll take QR, again, QR plus IQR. This is vector Q, which is n dimensional. It's a column vector living in n dimensions. The real parts are in vector QR and the imaginary parts in vector QI. Now take those two vectors and stack them on top of one another, QR, then QI. And so that's now a real value vector into n dimensional space. We can rewrite here these two equations as a matrix, which is 2n by 2n. So this matrix is 2n by 2n, and it is CXX here minus CYX and QRQI. Let's check that this gives the first equation. CXX times QR here plus minus CYXQI, that's here. This is lambda over 2QR. CYXQR, which is here, plus CXXQI, this part here, is equal to lambda over 2QI. Now, stare at this matrix, you will discover that it is exactly the covariance matrix of vector W. Okay, so this is CWW, which we have here. Note that the vector that we have here is exactly the vector that we have here. This is an eigenequation for CWW. We started with lambda and Q, an eigenpair of CZZ. Lambda is an eigenvalue, and the corresponding eigenvector is Q. Q is QR plus IQI. Now we have CWW times this vector is equal to lambda over 2 times the same vector. So lambda over 2 is an eigenvalue of CWW. And an associated eigenvector is the eigenvector constructed from Q by taking the real part as the first n components, followed by the n imaginary parts. From this, we can like sort of make a guess that CZZ is an n by n matrix. So it has n eigenvalues. CWW is 2n by 2n matrix. So it has 2n eigenvalues. So perhaps what is going on is that every eigenvalue of CZZ becomes repeated twice for CWW and divided by 2. In other words, that if we have lambda Q is an eigenpair for CZZ, then CWW will have an eigenpair lambda over 2 and QR QI, and lambda over 2 again as a repeated eigenvalue, and then another vector that is linearly independent of that vector. Indeed, this is the case. Take the matrix CWW and multiply it by the vector, which is a column vector in 2n dimensions, QI and minus QR. Note the following. So we have vector QR QI. This is what we have here. Note that if we do the inner product between this vector and this proposed vector, what do we get? So this is QR transpose, QI transpose times QI minus QR. So this, if we do the multiplication, this is QR transpose QI plus QI transpose minus QR. So we can change this to a minus sign QR. And for real valued vectors, QR transpose QI is exactly equal to QI transpose QR. So this is equal to 0. In other words, that this vector that we are using here is orthogonal to this vector. So they are linearly independent. And if we do the multiplication, if we take CWW times this vector, we get the same vector back multiplied by lambda over 2. So in fact, if lambda and Q is an eigenpair of CZZ, lambda is an eigenvalue that is real valued and non-negative, we will take it to be strictly positive, and associated eigenvector Q. Now, this for CWW becomes a repeated eigenvalue, lambda over 2, that is repeated twice, and it is associated with these two linearly independent vectors, QR and QI, and then the other one is QI minus QR. So the good news here is that the eigendecomposition of CZZ and CWW, these two eigendecompositions are very related. And this will allow us to rewrite the PDF and the characteristic function in terms of Z and its statistics, the mean vector mu Z and the covariance matrix CZZ. Okay, so for example, now, what is the determinant? The determinant of the matrix is the product of the eigenvalues. So for CZZ, let's assume that the eigenvalues are lambda 1, lambda 2. Those are not necessarily distinct, okay? But we'll give them different names, but perhaps 2 of them are equal and so on. So determinant CZZ is lambda 1, lambda 2, all the way to lambda n. It's an n by n matrix, and it has those n real valued positive eigenvalues. The product is the determinant. Now, for CWW, which is a 2n by 2n matrix, lambda 1, now it will appear here as an eigenvalue lambda 1 over 2 repeated twice, and so forth. So if we compute the determinant of CWW, we multiply the eigenvalues. So there will be lambda 1 over 2 squared, lambda 2 over 2 squared, all the way to lambda n over 2 squared. And so this is the product of the lambdas squared over 4 multiplied by itself n times over 4 to the n. And the product of the lambdas is the determinant of the covariance matrix of random vector Z. And we have a square here divided by 4 to the n. So this is a relationship between the determinant of CWW and the determinant of CZZ, specifically the determinant of CWW, which appears in the expression of the multivariate Gaussian PDF. This determinant can be replaced by another determinant involving the covariance matrix of random vector Z, determinant CZZ squared divided by 4 to the n. But in the expressions of the joint PDF and the joint CF, we also have quadratic forms. What should we do with these quadratic forms? The trick again is to employ the eigendecomposition of CZZ. CZZ itself can be written using its eigendecomposition as a sum over its eigenvalues and the outer products of its eigenvectors. So CZZ, it is lambda 1, and if Q1 is an associated eigenvector with lambda 1, then we have lambda 1 Q1 Hermitian, and then plus lambda 2, and if an associated eigenvector is Q2, then we have here Q2 Hermitian, and so on. The inverse of the matrix CZZ, assumed to be invertible, assumed to be positive definite, will be the exact same form, but the eigenvalues of the inverse are the reciprocals of those lambdas. And those are positive quantities, those are positive quantities. And so we can write down CZZ or CZZ inverse in terms of the eigenvalues and the associated eigenvectors. Okay, so CZZ is basically a matrix Q times lambda, Q Hermitian. And so this Q, it has the eigenvectors as its columns, and then lambda is a diagonal matrix of the eigenvalues. And then we have here Q Hermitian. Q Hermitian is the inverse of matrix Q, because Q is a unitary matrix because the eigenvectors are orthonormal. So the inverse, if we take the inverse will be Q Hermitian inverse is Q inverse inverse, that's a Q, and then lambda inverse is lambda inverse. We take the reciprocal of each element on the main diagonal, so those will be the reciprocals of the eigenvalues, and then Q inverse, which is Q Hermitian. So if we write CZZ using this sum, CZZ inverse can be written as this sum. And we find that we have here and there, we have QK Hermitian, and QK is an eigenvector associated with the eigenvalue lambda K. Now we are interested in taking this matrix Z and involving it in a quadratic form. So we will take D Hermitian CZZ D, or D Hermitian CZZ inverse D. So when we do this, D Hermitian will be multiplied by QK Hermitian, and from the other side we will have D. So we want to investigate this quantity. Again, because vector D will be multiplied here, so we'll multiply from here by D Hermitian and from here by D. So this QK Hermitian will be multiplied by D Hermitian and D. And we are interested in this quantity and whether it can be rewritten in terms of CWW, so that we can do the substitution and go, replace the stuff related to CWW in the PDF and CF expressions by the mu Z and CZZ. Okay. This quadratic form, so we have this is an inner product and this is its complex conjugate, so we can write down this as QK Hermitian D, the magnitude squared. Now each eigenvector, let's write it down as a real part plus I times an imaginary part. And so QK Hermitian will be QKR transpose and then QKI transpose. And because we have Hermitian, then this plus I becomes minus I. And then we multiply by D. Let's assume that D has a real part dr and imaginary part di. We have this product here. Multiply, so we get 4 terms. And then we can collect the terms. We have QKR transpose and QKI transpose. We can combine them in the same row vector, and then we have dr and di as one column vector that is 2n dimensional, and we can do the same to these 2 terms. And so we have now a real valued quantity minus I times another real valued quantity. So that's a complex quantity, and we take the magnitude squared. So we take the square of the real part plus the square of the imaginary part. And we can express our final result using vectors qk bar and qk tilde. Qk bar is basically qkr and then qki. So that's an 2n dimensional vector. And the first n components are QKR, and the second half will be QKI. QK tilde is also 2n dimensional, but then on the top it has QKI, and then the bottom n components are minus QKR. Let's go back to this CZZ. Again, the objective is to multiply it from the left by D Hermitian and from the right by D, and we should do the same here to have a quadratic form. And so this quadratic form, if we take D Hermitian CZZD and then we multiply by half, then we will have this summation. We multiply by half, so lambda K will be multiplied by half, like here. And then we make use of our result here. So this D Hermitian QK Hermitian D will be replaced by this quantity here, as we can see. Now, what is this summation? This summation is summation K from 1 to n, lambda K over 2, and then we have QK bar transpose plus QK tilde transpose. The kth term here can be written as lambda K over 2, then QK bar transpose, and this is an eigenvector associated with lambda K over 2, which is an eigenvalue of CWW. And then it's a repeated eigenvalue, so it appears again, and an associated eigenvector that is linearly independent of qk bar is qk tilde, which in fact is orthogonal to qk bar. And so here we have qk tilde transpose. Effectively, we have a summation with two n terms involving the eigenvalues of CWW and the associated eigenvectors. This is the eigendecomposition of matrix CWW. Now, if we use this result regarding D Hermitian QK Hermitian D and use it here after multiplying by 2, then we have the summation, and now we will have lambda k over 2 inverse and the eigenvectors. So this summation effectively is a sum with two n terms over the eigenvalues of the inverse of CWW. This is CWW inverse, expressed into using its eigenvalues and the associated eigenvectors. Now we have everything needed so that we write down the PDF and CF using Z and its statistics. Here is the original PDF. Here is the original CF. Now, can we write the PDF, the multivariate PDF, using Z? Yes. For the determinant here, we can replace it. It's under the square root. We can replace it by our previous result, that the determinant of CWW is the determinant of CZZ squared divided by 4 to the power n. And this gives, when we take the square root, we get the determinant of CZZ divided by 2 to the power n. And this 2 to the power n will eliminate the 2 to the power n that we have here. And so the outside factor in the PDF now becomes pi to the n, and we have determinant of CZZ without a square root. Now for the quadratic form involving the inverse of CWW, it is double the quadratic form involving CZZ. We take this quadratic form here, we combine these guys as a complex valued vector. So we'll have x minus mu x plus I minus mu y. Okay, let's actually write it explicitly. So we'll have one vector x minus mu x plus I y minus mu y. And then we have Hermitian CZZ inverse. And then we have the vector again d, and d is these two guys combined as an n-dimensional complex valued vector. So here we'll have x minus mu x plus I y minus mu y. This is nothing but z minus mu z. And then we have CZZ inverse, and we have Hermitian here it is, and then here we have z minus mu z. And there is a 2 here. So this expression will be replaced by 2 z minus mu z Hermitian CZZ inverse z minus mu z. The 2 will eliminate this 2 here. We have obtained the PDF of the complex valued circularly-symmetric Gaussian vector Z. Now it is written in terms of Z, its mean vector, and its covariance matrix CZZ. Last thing to do is to rewrite the characteristic function also in terms of the statistics of vector Z. Now we have a quadratic form, and this quadratic form, it involves vector a 2n real valued vector, which is vector u bar stacked over u tilde. And according to this result here, we can combine u bar and u tilde as u. So we can define u now as an n-dimensional complex vector, and u is equal to u bar plus I u tilde. And we take this quadratic form and replace it by 1/2 u Hermitian, 1/2 u Hermitian CZZ u. So we will, because there is a minus half here, we end up with minus 1/4 u Hermitian CZZ u. The last part to handle is this part. How can we express this part in terms of vector u? Now, if we take the inner product of u Hermitian and uz, so this is u bar transpose minus, because we have Hermitian, minus I u tilde transpose times mu x plus I mu y. Now, we have u bar transpose mu x, which is this, and we have minus I times I u tilde transpose mu y. This will give us u tilde transpose mu y, and that's it. So to get these two terms and nothing else, what we should do is to have the inner product of complex valued vector u with mu z, and then take the real part.